Okay, YouTube, in this video, what we're going to be doing is focusing on the power of inverse trig functions to help us solve for angles when we want to know angles. If we know a trig function value, awesome. Let's go find the angle. So what we're going to do is look at an application problem here, I suppose. It's kind of nice to review angles of elevation and depression, how we kind of set that up. But basically, let's go ahead and read through this here and talk about how we can use an inverse trig function to our benefit to find an angle. So we would say that a plane is flying at an altitude of 20,000 feet, locates a radio control tower from its position. It says if instrumentation shows the straight line distance from the plane to the tower is 500,000 feet, what I want to do is determine the angle of depression between the plane's horizon and the radio control tower. So that is to say that, well, I'm guessing that there's probably a right triangle involved here. Now, not to say that we can't ever work with oblique triangles, but I kind of see this as a situation where maybe, perhaps, our plane is up in the air. We say our plane here, there spots a tower off in the distance, essentially. And so what do we know about this situation? Well, we know that 20,000 feet is the altitude of the plane in a straight line distance. This is not the horizontal distance from underneath the plane to the tower, but we say if you connected them with like a laser beam there, we would say that this is 500,000 feet. And so essentially what we want to do is go find the angle of depression. Now, recalling that angles of elevation and depression all are being compared to this imaginary horizontal line that we just refer to as the horizontal. So that is to say that, an angle of elevation would look something like this. We say elevate, some positive angle that goes up from the horizontal. An angle of depression would go down from the horizontal. So we'd say that this is still, when we talk about angles of depression or elevation, we say they're always positive. We're not going to get into arguments about which way you rotate it. But basically, that this angle is going down from the horizontal. So when we say that I want to find the angle of depression between the plane's horizon and the radio control tower, we always kind of assume that, if this is my head here, kind of make a little face there, that's really creepy. But we'd say that the horizon is always in line with your perspective, where your eyes are. So that is to say that if our plane is flying along here, then the plane's horizon, let me see if I can make this a little bit straighter here. The plane's horizon is this imaginary line that runs through the pilot's eyes, whoever he or she is. So when we discuss an angle of depression, what we're really saying is that we want to go find this angle right here, which interestingly enough, I'm going to call theta, it's not inside the triangle. So what we're going to have to do is borrow from geometry a little bit here, but say that this horizon here is parallel to the, I suppose, the ground here. We say these two are parallel. And the reason why that might be important is essentially because remember that with these two parallel lines, we can look at the hypotenuse of our triangle here. Let me see if I can sketch on top of it here. As being a transversal that kind of cuts these two parallel lines. And so because it is a transversal that cuts across two parallel lines, then I know that this angle down here really is my theta. These two alternate interior angles would have to be the same, okay? So what we're going to do here is essentially this. We're going to call this down here our angle theta, but because we know it has the same values as our angle of depression, then we're going to say we're really finding the angle of depression. So let's set this up here. I do realize that, with respect to theta, the sides that we know lengths for here are opposite in the hypotenuse. And so it is most appropriate to use a sine relationship. We're going to say sine of our angle is essentially our opposite side, so 20,000 feet over 500,000 feet. So 2 with 4 zeros, 5 with 5 zeros. First thing I'm going to do is I'm going to cut out a factor of a 10,000, divide them both by 10,000. And so it becomes the case that we get sine is really a value of 2/50ths. I got a little ahead of myself there because what I want to call this is now 1/25. But basically, it is very fair to say that our equation is the sine of theta equals a half. And so now, what is our job? Well, our job is to go and solve for theta here. And so, sorry, not 1/2, 1/25, yikes. But our job is to go solve for theta. So really, all of this setup here was just to use inverse trig function to go solve for this value. So to get theta by itself, we have to undo our sine. And to undo our sine, what we're going to do is this. We're going to take the sine inverse of everything on the left and the sine inverse of everything on the right of this equation. And we see that on the left side of this equation, we had a sine theta. On the right side of this equation, we had a 1/25. We'd say if we take the sine inverse of both sides, then this equation is still equal. And what do we know about sine inverse of sine? Well, because they're inverses, they undo each other, and we get left with this theta equals sine inverse of 1/25. So the fabulous thing here is this. This, by the way, is the exact value of this angle. The exact value is literally the angle is the angle that you get when you take the sine and you get a value of 1 over 25. It's kind of a stupid thing to say. It says, well, I'm the angle that when you took the sine of me, you got 1 over 25. And it's like looking at this picture, it's like, well, yeah. But I mean, what is the measurement of this angle? And so not to leave you hanging here, basically what we're going to do is this. You got to get your calculator out, and your calculator is going to answer this question for us. As a matter of fact, we're just going to type in sine inverse of 1 over 25. And so first things first, with respect to your inverse trig functions, let me quit out of this menu here. Your inverse trig functions on the calculator here, at least with TIs, are right behind your regular trig functions here. And so if I want the sine inverse of 1/25th, I'm just going to type in the sine inverse of 1 divided by 25. Now the other thing about this is, I'll go ahead and click enter, is this is the angle. Now the fact here is my calculator by default, if I go into mode here, is in radian mode. So you can tell somebody that this is a really shallow angle of depression. I mean, hey man, it's about 0.04 radians, which is not a lot, but we usually talk in degrees. So here's what we're going to do. Mode. I'm going to flip over to degrees and say, okay, so dear calculator, would you tell me this again, but tell me in degrees. So I'm going to hit second enter, which retypes in the last thing I typed in. I hit enter again. And what I get is about 2.29. I'm going to call it about 2.3. So if I were to go up here to my picture, well, first of all, let's write this here. We'd say theta is approximately 2.3 degrees. So we'd say that this is my approximate value, and a little bit different than the exact value, but if I go fill it in now on my picture, we say this is about 2.3 degrees, so up here I'll put it in the same color as this tealish color, about 2.3 degrees. Is this reasonable? Well, yeah, to say that the hypotenuse was 25 times the length of the height of the plane, and man, it was flying at 20,000 feet. So yeah, I'm guessing this radio control tower is way off in the distance and their angle of depression is reasonably small. Cheers.